As I have mentioned, the explicit proof for jackknife and its asymptotic properties is beyond the scope for this class. However, let me give some intuitions about why the jackknife works and when it works. Let's first consider the case where our estimator for theta hat, is unbiased. In other words, the expectation of theta hat is equal to theta. Then obviously theta hat bar is also going to be unbiased estimator for theta, because each of the theta hat i's will be unbiased, and so will their sample mean be. In this case, we can see that the jackknife estimator for the bias of theta hat is given by n minus 1 times theta hat bar, the expectation of theta hat bar minus theta hat. And this thing also has expectation of 0. In other words, when theta hat is unbiased, then the expectation of the jackknife estimator is also going to be equal to 0 for the bias. But this case is not very interesting. Let's consider the other case where theta hat is actually biased. If theta hat is biased, then in this case we can write the expectation of theta hat as theta plus a divided by n plus b divided by n squared plus etc. So this is essentially the series expansion of theta around theta hat. Here, a and b are functions of the distribution of x, so the fx, which does not involve the sample size. The terms in blue over here, so theta plus a divided by n, is known as the first order Taylor approximation, or the linear approximation for the expectation of theta hat. So subsequently, the first order approximation for the bias of theta hat, which is the expectation of theta hat minus theta, will be a divided by n. So what is the expectation of the jackknife bias estimator in this case? Let's first note that the expectation of theta hat bar is the expectation of the sample mean of the theta hat i's. And this will be equal to theta plus a divided by n minus 1 plus b divided by n minus 1 squared, etc. So just like the case for the MLE for variance, nothing changes in the series expansion except for the denominator, where we replace n by n minus 1. Once we know the expectation of this guy, we can try to find out what is the expectation of the bias estimate using jackknife. Thus, the expectation of the jackknife bias estimate is equal to the expectation of n minus 1 times the difference between these two. And this is equal to n minus 1, we pull out the constant, times the difference between the expectation of theta hat bar minus the expectation of theta hat. Expectation of theta hat bar is equal to this guy, and expectation of theta hat is what we had on the last slide. Plugging these in, we get the following. You can see that the thetas will cancel out, and we are left with n minus 1 times a divided by n minus 1 minus a divided by n plus something of order of n to the negative 2 power. So in this case, you can see that this will be equal to n minus 1 times a divided by n times n minus 1 plus something which has order of n to the second power beyond, so n to the third power or n to the fourth power. And in this case, the numerator and the denominator cancel out, and you're left with a divided by n plus something of higher order. As our sample size increases, you will expect the n squared to increase. So as the denominator of these guys increase, the later terms will become smaller and smaller and start to vanish. So what does this tell us? This tells us that the jackknife estimator for the bias of theta hat is accurate up to the first order. Its expectation is equal to a divided by n plus something, which is, you can see that the first term is the same as the first order approximation for the bias of theta hat, which is a divided by n. That's what we mean by this jackknife estimator will be accurate up to the first order. The earlier example for MLE of variance estimator that we have seen has bias of exactly a divided by n. In other words, there are no later terms of the bias. This a divided by n is the last term. Specifically, it's negative sigma squared divided by n. So in this case, the jackknife bias estimator is unbiased. So it's accurate up to the first order. The first order is exactly the bias. So in this case, the jackknife estimator is unbiased. However, in general, when your bias is not exactly a divided by n, the jackknife bias estimator is not necessarily unbiased. This also tells us when jackknife will not be appropriate. You can see that the proof or the intuitions behind jackknife estimator for bias involves the Taylor series expansion of theta around theta hat. So when the statistic or the estimator theta hat is not a smooth function, in other words, intuitively, it's not continuous and differentiable, then we cannot use the series expansion, and the jackknife in general will not work. An example for this is the sample median, which is not a smooth estimator. If you're interested in this, you can look at the example on the result book, so example 7.8, which demonstrates this. And you can see that the jackknife estimate of the bias of the median is going to deviate from the true value.